Okay, for the force current analogy or the parallel analogy, we will derive again or determine what are the terms or components that are analogous between the two systems, the mechanical, translational, and the electrical system. And to do that, because this is a parallel analogy, so we can just start with a parallel circuit. So if we have a parallel circuit, we have R, we have L or C, capacitance, and we have an inductance. All connected through, because this is a force current instead of a voltage, we see current source. Here we see current source. I is of T. And this is R, this is L or C, and this is L. Then to determine the transfer function or the of this system, the equation of this system. So we all know that the voltage across all of these components are the same. And this will be, this call it is of T. Now in this analogy, our input now is the current and our output is the voltage. So it's the other way around because we are taking the force current analogy. So if the current is the input, the output now will be E, will be changing with respect to that input. And to solve for that voltage with respect to the I here, we can just first solve for the equivalent impedances for these three. So for R is just R, C is 1 1 over SC. So let's just draw it in red. 1 over SC. And this one is, this is S times L. So these are the impedances. Then apply our methods in circuits. So if we add them all the impedances, and multiply it with the voltage E, that will be our current I. And we will be adding the inverse of all these components. So this will be the voltage is of T and multiplied with all the components connected to that node. We have 1 over R plus 1 over SC. So that will be just SC. So I can just change this one. Let's go directly to the S domain. So E now in S domain. We multiply it with R, or should I mean the inverse of R? It should be inversed. So it should be 1 over R. 1 over R. Then we have plus these impedance 1 over SC. That's just S times C. Then plus for this one 1 over S times L. And this should be equal to, this is the equivalent or the inverse of all these impedances, and this should be equal to the current I of S. Now if we go back again to the uh, translational mechanical system, so the translational mechanical system, so you have a spring, a damper, and the mast M. Then we apply first F of T. Then we have a displacement X. And we already derived the equation of this before in second order system, the mass spring damping system. And that is equal to, let's just look at it here, translational mechanical system. We already derived that. And here it is. Let's copy this one. Then I'll go back here. Then paste. Then change this one into, oops. Wait. Okay. So this is the equation of a mass spring damping system. So if we try to observe or uh, these two, observe these two equation. So let's just inverse this. I'll rewrite this one because I put I here. Then E is our output here. Then I'll just copy these three. Then I can multiply S. You can multiply S here. So if you do that, if I multiply S, what will happen? I need to divide it by S also. So what will happen here? So if I multiply S, this will S squared, C S squared, then plus we have 1 over R times S, and we have here 1 over L. But I did multiply S in this equation. So I did multiply S, so I need to divide here also, or multiply also S at this part to compensate that. But in the translational mechanical system, if we change this X instead of X, we change it into velocity again, just like what we did in the force voltage analogy. Or instead of changing this one, we can just change this force here. We can force this one to be in this format. We have a constant here, so we already have a constant ks, and we need a term that has 1 over s, and here we don't have a 1 over s. So what we do is we divide this one by s. So I need to multiply here by s, and I need to divide this by s. So the equation now, f of s will be s times x of s. This will be m times s squared over s is s, plus k spring constant divided by s, plus this will cancel out k d, or the damping constant, or the viscous damper. So if we look at now here, but we have s times x of s. And remember, what is displacement? What is displacement? What is velocity? Velocity in time domain is just equal to the derivative of the displacement with respect to time. So if I take the Laplace of this, v of s, or the velocity, will be just equal to s times x of s. So we can just change this into the velocity. So the equation will become f of s equals velocity in s domain, then multiplied it with this one, ms plus ks over s plus kd. Then we go back to the electrical equation here. If I rewrite that into this format, so our output I is of s, then this is the voltage is of s, then a term that has s in this one, that is sc, so this will be c times s, plus the term that has 1 over s in this equation, and that is 1 over sl. 1 over s times l. Then finally, the constant in here, it's just 1 over r. 1 over r. And by inspection, from this equation, we can now identify the analogy between these two. Because this is a force current analogy, so force and current are equivalent. This is not voltage, this is velocity, and the voltage are equivalent. The mass and the capacitance, Ks and 1 over L, Kd and 1 over R. 1 over R is the conductance. So from that, what is now our analogy? So these are our force current. Force current. The force F is equivalent to the current I. Then number 2, the velocity. Velocity, which is the x dt. The x dt is now equivalent to the voltage. V. Then the mass M is equivalent to the capacitance C. Number 4, the uh, spring constant Ks. Spring constant is equivalent to, this Ks is equivalent to 1 over L, inverse of the inductance, or reciprocal of the inductance. There's no such thing as the reciprocal of inductance. Although in circuits 2, because the reciprocal is 1 over Henry. If you remember in magnetic circuit, the unit for reluctance is also 1 over Henry. But some of the books don't acknowledge that. SI system, unit system, don't acknowledge that unit. So therefore, instead of saying that the reciprocal of inductance is the reluctance, unlike the, if you remember the elastance, the unit for elastance is daraf. So if you look at that, this is just like similar with the conductance and the resistance. The unit before the resistance, unit of resistance is ohm, while the unit for the conductance, the inverse of resistance, is mho, mho. Here, it's also similar with that case. The unit of the elastance is daraf. It's just the mirror reciprocal of the capacitance, which is also 1 over C. But for inductance, this is just 1 over L. Instead of using reluctance, I just use this reciprocal of inductance. And lastly, for KD, spring or the damper coefficient or constant, or the viscous damper or damping constant, KD, this is equivalent to 1 over R, or that is the conductance. 1 over R. So these are the equivalents in force current analogy. Now let's try to create again the circuit of the previous example from the force voltage analogy, the series analogy here. So our example here, I'll just copy this one. Instead of using the series analogy, let us now use the parallel analogy. So what are the components here? Then remember our rules in determining the analogy between the two systems. The number of masses is equivalent to number of mesh. Also, but this time, because this is a force current analogy, our common element, these two here, instead of connecting them in common in between, there will be in series between the two. So for the first two here, so our input now will be a current source. This is FT. Then instead of a series, it's a parallel. So we have the wait, we start with the mass. What's the mass? Mass is equivalent to the capacitance. So this will be the capacitance. This is mass. Then we have what's next? The inductance. This one, the spring constant, is equivalent to the reciprocal of inductance. So you have the spring constant. One over L. Then for the resistance, or the conductance, which is 1 over R. So this will be 1 over R. And now, before in the force voltage, we connect them in the common is in this position. But this time, we connect them in series. So this will be in this format. We have the two components, the spring constant and the damping. So the spring constant, reciprocal of the inductance, and the damping is just the conductance. So reciprocal of the inductance, and this one is the conductance. This is one over uh R here. Or wait, instead of L, why did I use L here? And 1 over R. It should be in terms of the mechanical system because we're solving for the mechanical system. So the inductance here, 1 over L here, is equivalent to the spring constant. So this will be 1 over K. 1 over K S. For this one, this is equivalent to 1 over KD. And for this will be, because this is KD, let's just call it 1. M1, KS1, KD1. And for the 1 in the center, this is 1 over, let's call it KD2, and this one 1 over KS2 for the spring constant here. Then for this right side, so we have again the mass. So this will be mass 2, and we have again the inductance is equivalent to 1 over Ks2, spring constant. And for the damping, it's equivalent to the resistance 1 over Kd2. And we connect them, and this will be the equivalent circuit of that problem. And remember, the voltage now is not is our output in this case, because our input is this current source here. So voltage here at this point, the net voltage at this point, this is actually V1, and this one here, the voltage here is our V sub 2 in T domain. So these V's here these are voltage, not the velocity. But actually they are equivalent also to the velocity. They are also velocity because here, remember, velocity is analogous to voltage. So we can treat them as just a velocity. So the solve for the V2 as our output, and this will be your homework. So this will be homework. Derive the transfer function of this using the circuit now that we derived, that we completed. So using any method in circuits, derive V sub 2 as all over f of s. What is V sub 2 as all over f of s? To be passed at MBLE. Okay?